Hello. Okay. Let me start with the topics here. The subject I have chose is the degenesis algorithm. This is a very important subject. It is the core subject of computer science. This is not only the knowledge point of view, or the only for the just yeah, uh, give examination and pass. It is very important for campus placement of view also. So the knowledge of this subject is very important in computer science, particularly for the computer science student. Here, what is this subject? See, okay. Okay. The subject is design analysis of algorithm. Basically, it has two main parts. One part is the analysis, and another is the design. The analysis part of the algorithm is very difficult one, and it is you need to know a lot of things for this. It is not easy thing to analyze the algorithm, but design the algorithm, we use various design method or technique to solve the problem. First, I just want to share the things, some important things regarding analysis. What are the things you need to remember or need to know every time while solving or while analyzing algorithm? The algorithm can be basically, it is two type. Basically, we say the algorithm is two type. What are the those two types? One, we can say the iterative algorithm, or you can say it is the non-recursive algorithm, and another one is the recursive algorithm. And the method of analyzing these two algorithms are different. Some points or some steps are common in both type, and some steps are all different. Like when we want to analyze suppose a non-recursive algorithm, or you can say iterative algorithm. The iterative algorithms are basically the algorithm which can having mostly the loop. So sometimes we find the loop complexity of that algorithm. Okay, so why this? Because the most of the iterative program based on the looping. Looping can, but this subject degenesis algorithm, don't know, it is a totally language independent subject. It doesn't depend on the language type of language you are using. So like data structure is also a language independent subject. It doesn't depend on the any language. Once you know the algorithm, you can implement that by using any programming language. If you have, suppose, if you have an idea of certain sorting technique, you can write code using any programming language. But whether it is a data structure or design analysis algorithm, both the subject are language independent subject. So here the understanding of algorithm is very important. If you know the algorithm, if you know the way of solving problem, how to solve the problem, or the steps required to solve a problem, this is basically the definition of algorithm. The meaningful steps to solve a problem, okay, or sequence of steps to solve a problem. If you know that, then that problem or algorithm can be easily analyzed. So I'm talking about your iterative algorithm. Most of the iterative algorithm contain the loop. So the main things is analysis. What are the things you need to know before analyzing the algorithm? First, see, for any algorithm, first we know what are the basic things. Suppose I want to calculate the time or determine the running time of an algorithm. running time of an algorithm. And that is nothing but the running time is nothing but the function of n, function as a n, where n is your size of input, where n is your size of input. So normally we find either fn or tn of any algorithm to determine the running time of algorithm. And that is very crucial and very difficult. It is not easy to find the running time or total run time of an algorithm. If it is given, if any function is given, then we can easily find the complexity of that, uh, uh, because every function must, if it is a given, every function must related to some algorithm. Okay. If we analyze the algorithm, then we can determine the function. But if function is given, function is given, to write the algorithm for it is again it is not easy. So both are not easy. If the algorithm is given to find that function as a function like fn or tn, or if tn is given or fn is given to write the algorithm. So both are not easy because it is a part of analysis. Now, what you do? Suppose if an algorithm is given and we want to find the complexity analysis of this algorithm. Complexity. Basically, we know there are two types of complexity. One is called space complexity, another is called time complexity. But we don't bother about the space complexity. The how much memory is required to run the algorithm. We don't bother for the how much memory is required. But the things is required. The algorithm, the performance of algorithm is mainly depend on its time complexity or efficiency of the algorithm. Efficiency of the algorithm. The efficiency of the algorithm again depends on what its time complexity. So time complexity is nothing but the t as a function of n. T as a function of n. So how do you find the time complexity of an algorithm? How do you find out the time complexity of an algorithm? Let me share the slide first here. See, this is the time complexity. Okay, we start with the time because the basic, very basic of the analyzing the algorithm. Time complexity is basically amount of computed time needed for the algorithm to run to completion. So it is a TP or maybe TN equal to CN plus RN, or TP is equal to CP plus RP. But CP is the independent problem instance and is always not required for its recompletion. And so usually only RP is considered. Like the another things is required for determining that or the basic step, for analyzing the algorithm. The very first is you must know what is the size of input. What is the size of input first? And that's normally the size of input for definitely an algorithm a size. Like suppose consider an array problem, any array problem. Suppose we want to find the maximum or minimum of a list of array, or for any searching problem like linear search or sequential search, or suppose for any sorting problem, we have to use array. For any matrix operations, we need to use array. So that array, if you're talking about the array, that array should have some size. The number of that is basically the number of elements in that array. So that gives the size of input. Next is what are the basic operations? What are the basic operations for analyzing the algorithm? What are the basic operations? So what are the basic operations? The basic operations are basically the operations which involve in the algorithm for solving the problem. Okay, so like for example, the basic operations can be any arithmetic operations, can be basic operations. Okay, any arithmetic operations like additions, multiplication, subtraction, additions, whatever that basic operations. Even the comparison is also basic operations. We can compare the two values. Comparison operations, any relational operation related to any relational operator or logical operator. Now another basic operation is your like indexing of an array index, that is also a basic operations. Calling of a function, returning a value from a function. These are all basic operations. So those are required for in order to the count, in order to find or determine the running time. Basic operations, is understanding of the basic operation very important. Then after knowing the basic operations, we need to count the how many times the basic operations, how many times a basic operation is executing. The number of times of a basic operation executing, that is also is required. That can be again as a function of n. That is suppose cn, the number of times the basic operation is executing, and that is the counting of the basic operations. And then finally we determine the tn, that is the tn as a function of n. That is the called total running time. Normally, suppose, for example, if we are talking about the linear search, simple example, linear search, and the very basic operation is which one is the basic operations? The basic, normally because we do not always we do not find the total running time of an algorithm, because it is very difficult to find the total running time. In order to find the total running time, you have to count each and every steps of the algorithm. Each and every step of the algorithm, whether it is an assignment statement or it is a loop. You have to count the, if there is a loop, then you have to count the loop heading, also the counting of the body of the loop. Okay, also you have to count the, if the function, any function contain the return statement, then again we have to count the return statement. If any function containing any mathematical operations or any assignment statement, that we have to count separately. We have to count the increment operation, because if you are using the loop, there is a increment. So everything you have to count to find the total running time. So normally we don't find the total running time. So in order to simply find the time complexity of any algorithm, so basic operations may suppose if it is a linear sequential search. So simple the operation is, suppose if an A is an array. Okay, if in A is an array and suppose X is the search element, the element to be searched X, then only the operation, which operation is set to be the basic operation? That is your AI is equal to X. If there is a loop for I equal to, suppose I equal to 0, and I less than and I plus plus, and then if there is a comparison statement, if AI is equal to X, that is within the loop, and that is called the basic operations. And that's why the linear search, then because if we are using only the single loop, only one loop, so finally we'll get the time complexity of the linear search is what? Order of n. Now how this the order, what do you mean by the order? Later on I will discuss what is that order, or big O. Normally we write the big O of n. So size of input and the basic operation plays the most important role to determine the time complexity. Normally the time complexity can be determined by using the asymptotic notations. I will discuss just after this what do you mean by those asymptotic. So this is the there is a loop, the number of passes the loop, then counting the basic operation or the steps in the loop. Because normally whenever we are talking about the analyzing of the iterative algorithm or non-recursive algorithm, basically the complexity depends on the loop, number of loops you are using in the program or in the algorithm. If there is a single loop, normally the time complexity will be what? Order of n. If there are two loops, it is order of n square. So that is important. But how it comes, order of n or order of n square? And there is a formula normally used, the formula for to get the your order of n square, order of n, or order of n cube, like that. So search, suppose basic operation compare, basically with comparing that x and y, searching matrix. There is again matrix multiplication. There is different time complexity. So time complexity can also be expressed in terms of the basic steps performed. So express as a function of instance characteristics, that is your input size, and output size expression. Now these are the steps in algorithm. Steps meaning full segment of a program or computational unit that is independent of the instant statistics. Some examples are like this. Now see that how it can be basically how do you determine the any running time of an algorithm. That is talking about the running time. How do you get the running time? Okay, this is a simple algorithm. The algorithm is used for the only the finding the sum of suppose it is an array of numbers and I want to find the sum of all the numbers from 1 to n. So see there, this as initially s is equal to 0, then I is equal to 1 to n, there is a loop, and then s is equal to s plus ei, and then return s, because this is the algorithm name, and the name parameters here. A is an array parameter and n is the number of elements in that array. So there are two parameters we have used for this, because the algorithm for analysis algorithm, the detail is not required. Suppose how to the input output statement is independent for analyzing the algorithm. It doesn't depend, because the input output statement doesn't depend on the your time. Things are your loop, the assignment statements, and the assignment statement consists of mathematical operations, many methods, and the return statements like that. So if you see the very first statement, there are, suppose that there are 4 steps here. This algorithm consists of 4 steps. The first step is s is equal to 0. The second step is the for loop, that is a for loop heading or header, for loop header. The third okay, so it's the your the complexity just I'm telling you, say there are different types of complexity, time complexities are there in terms of big O. In terms of big O, later on I will discuss about big O. What is if it is a suppose big O of 1, that means it is a constant time complexity. Big O of 1, that means it is a constant time complexity. The constant time complexity is basically that's one basically the like your assignment statements or returning value from a function, that is the constant time complexity. So s is equal to 0, if the big O of 1 is simply 1. Then for I equal to 1 to the loop is executing for n number of times. So it is obviously n. 1 to n means n times. Why it is n plus 1? Because the purpose of using loop is not to only execute the body of the loop. It also will count the that thing for which the again when the we can exit from the loop. So that is the n times the body will be executed, and if it is n plus 1, that means the we can come out from the body. So that's a testing part. How many times the loop will be executed, and that is. But when we're talking about the header, loop header, so the also the we count that when the loop will be, when we can exit from the loop. That's why it is n plus 1, n plus 1, and s is equal to s plus I. That is again one single assignment statement, and this body is executing for n time. So it is order of n. Okay, and the return statement, because you are returning a value from the function, so again it is a single statement. Return a single value, so it's your order of 1. So when we count this, when you count or sum this, so you will get it is 2n plus 3, and this gives the tn, and this gives the tn, the value of tn. That is tn is the running time or runtime of an algorithm. Tn is equal to 2n plus 3. So in this way we can find the runtime. This is a very simple example. An algorithm having a single loop, and the problem is nothing but to calculate the sum of numbers. Next loop, suppose is it contains two loops. If you see there are two loops, and we are adding. That's example is the addition of two matrices of same order. Basically, we can add two matrices only when they are of the same order. So here normally, although we have used that there are two loops and their size is different here. One for I equal to 1 to m and 1 to n, and Cij is equal to Aij plus Bij. Normally, both are m. We can add two matrices if they are of the same order. So again, when we are counting, the outer loop executing for m plus 1 time, the inner loop will be executing for m times plus n plus 1, because inner loops again executing for n plus 1 times. But for each inner loop, the outer loop will executing for m time, because the inner loop is the body for the outer loop. The inner loop is body for the outer loop. So inner loop will be executing for how many times? For the m times, that's why n. Inner loop is executed for n plus 1, but the outer loop, for the outer loop it is body, so it is m times n plus 1. Again, the assignment part will be executing for how many times? M into n, because it is again it is a body for the inner loop as well as for the outer loop. So it is m into n. When we add them, so you will get 2 times mn. See here, mn, there are 2 mn and 2 times m plus 1. So this is again the value of tm comma n, that is a running time. But if m is equal to n, then it is a tn, then tn will be what? It is a 2n square plus 2n plus 1. If suppose m is equal to n, then it is 2n square plus 2n plus 1. So it is the running time of this algorithm. So it depends on the algorithm, when we are analyzing the algorithm, totally it depends on algorithm, that what is the behavior of the loop. So because the iterative algorithm mainly depends on the loop complexity. So in this way we can count the steps, all the steps to get the running time of an algorithm. So similarly, so another algorithm is there. So all are different algorithms here. So here the sum will using the recursive. It is a recursive algorithm. So see, recursive algorithm, again here we're getting the time complexity, different one, like 2 plus x. We are calculating the if n less equal to 1, then this time complexity 1. The return 0, that the time complexity is 1. And then inner loop, else there is no loop here. There is no loop, so its behavior is different. So it is a part of normally recursive algorithm also, because it is part of, because r sum is a function, and you are calling r sum within the function. So it is an example of a recursive algorithm. So again, the recursive algorithm, analyzing a recursive algorithm is different. Now see, this is the graph. I'm talking about there are the efficiency classes. There are different efficiency class, like if constant efficiency class, constant with time complexity is order of 1. Then your linear time complexity order of n, linear time complexity order of n. Quadratic time complexity, it is order of n square, quadratic time complexity. And then your logarithmic time complexity, it is log of n. Logarithm time complexity, log of n. Similarly, you have the n log n time complexity. The n log n time complexity is what? Your n log n, that is linear logarithmic. N log n is linear logarithmic. Then you can time complexity order of n cube, also n cube. Then again the highest time complexity, that is your exponential time complexity, that is 2 to the power n. 2 to the power n. So 2 to the power n is the time taken by the 2 to the power n type of algorithm takes more time than any of the algorithm. The exponential time complexity takes always the more time than any of the algorithm. So if we write them in order, in particular order or ascending order, the very first one is the constant time complexity. In ascending order, constant time complexity. Then your order of n, then order of it is log n, then order of n log n. Okay, then order of n square, then order of n cube. Okay, and then finally it is order of 2 to the power n. So in this way we can arrange them. The different efficiency classes can be arranged. Now there is a the example is also there. Suppose you are talking of the constant time complexity order of 1. Simply it is a constant time complexity is the any assignment statement. Simple assignment statement is an example of constant time complexity. Any assignment statement or even a return statement, that is also a constant time complexity. If you are talking about your linear time complexity, the example is your linear time complexity or is your linear search, okay, or simple any search. Similar or adding up, in which we can use only single loop, basically linear time complexity. Then your logarithmic time complexity. Logarithmic time complexity is basically uses the certain design technique, log n, and when we divide the problem into the subproblem, then normally for those cases the time complexity is either basically using the divide and conquer technique, design technique. So the time complexity is normally either it is log n, logarithmic, or n log n. So for already maybe the logarithmic time complexity log n, it is a binary search. If you know the binary search, the time complexity is what? It is a log n. But what is the base when we are representing any log? What is the base? Is it 10 or 2? What is the base of the log? It is not 10. It is base 10 is used for the common logarithm, but here the base is 2. Log n base 2. Why base 2? Because we are dividing the problem every time. We are dividing the problem into, suppose there are 8 number of elements are there in an array. So first time we divide 8 by 4, then 4 by 2. So every time we are dividing. So it is after k step, it may be 2 to the power k is equal to n. Suppose every time suppose we start for the number of elements n is equal to 16. So when we divide the 16 by 2, it becomes 8. When 8 is divided by 2, it is 4. When 4 is divided by 2, it is 2. Again, when 2 is divided by 1, then finally it becomes 1. So after k step, that it becomes what? 2 to the power. It is in the form of, when we represent it in the form of binary tree, basically. Okay. Root contains single, then 2 children. Then again, when divide, each node contains 2 children. So when you see that it is first time it is 2 to the power 0, that means 1. Then 2 to the power 1, it is there are 2 elements in the first level. In the second level, there are 4 elements, 2 square. In the third level, 8 elements to the power q. So after k step, it becomes 2. So that's the binary tree, example of binary tree. So 2 to the power k is equal to n. Therefore, n is equal to what? According from the definition of logarithm, if 2 to the power k is equal to n, okay, then k becomes n log 2. So n log n base 2, log n base 2. So that's why the logarithm of base 2. So for binary search, it is log n base 2. For either it is quick sort or merge sort, there are various sorting technique. Some of the sorting techniques are time complexity big O of n square. Some of them are big O of what? Big O of n log n. So that is a big O of n log n, either quick sort or your merge sort. Both are using your divide and conquer technique. Similarly, your n cube matrix multiplication, example is your order of n cube. The example is matrix multiplication. Similarly, 2 to the power n, there are many problems in design technique with time complexity is 2 to the power n. I will come after some time. What kind of algorithm or what kind of problem with having time complexity order of 2 to the power n. So these are the. Okay, now come to the basically the asymptotic notation. I am talking about your asymptotic notation. What is asymptotic notations? That is very important for analyzing the algorithm. Without this, we cannot analyze the algorithm. So this notation, asymptotic notations, the most commonly used notation is your big O notation, and big O notation is mainly used for testing the upper bound of a function. So the mathematical definition is there. This just understanding of this, because without having the idea of notation, asymptotic notation, particularly big O is most important one. normally perform the big O or big theta. Big O or big theta. Okay. In some book you will find that is a big theta, or some book you'll find a big O. So big O is basically used for this is a notation which is used for the worst case analysis. There are three types of analysis, you know, worst case analysis, best case analysis, and average analysis. Mostly we perform the worst case analysis. Okay, some of the cases we also perform the best case analysis, but worst case, in the worst case analysis, big O notation is used. In your best case analysis, your theta notation is used, and another notation that is called omega notations, which you can also use there. So Fn is equal to big O of Gn. This is the mathematical definition. Fn is equal to, and Fn and Gn are two non-negative functions. But the value of Fn and Gn should not be less than 0. Remember, the value of Fn and Gn should not be less than 0. It is always 0 or greater than 0. So that's why it is a non-negative functions of n, Fn and Gn. So Fn is equal to big O of Gn, or Fn is said to be big O of Gn if there are positive constant n0 and c such that, okay, such that Fn is less or Fn, which Fn is less or equal to Cgn, or you can say Fn 0 is less or equal to Fn, 0 is less or equal to Fn, or Fn is less or equal to Cgn, where C and 0 both are positive constant. Positive constant means both are greater than 0, and n is greater than equal to 0. N is greater than equal to n0. So see here, this is the graph for your big O notation. This is used for the upper bound. That's why Cgn is just above your Fn. Fn is just below the Cgn. That's why it is called upper bound. Gn is above the Fn. But what suitable value of C? Gn is greater than Fn. That we have to determine. The important thing of this notation is to determine the value of C and n0. The value of C and n0. So once you determine the value of C0, and that function must satisfy this, Fn is less or equal to Cgn, then only we can say Fn is equal to big O of Gn. So this is an example. See, big O notation. Suppose n square equal to 10n. Some algorithm having this. Fn is given. Fn is equal to n square plus 10n. Then it's because in big O notation, you know, it is a polynomial. Basically it is a polynomial. So polynomial highest degree polynomial, always the highest degree polynomial gives the big O notation. So highest degree means the terms containing the highest degree, that is n square. So n square, big O of n square is the, for this function it is a big O of n square. If it is any function 5n3 plus 6, then big O, it is a big O of n cube. Then 3 log n plus 8, it is a big O of ln, big O of log n. If it is n square plus 10n, then it is a big O of n cube, or big O. Normally it is a big O of n square. Last one is also big O of n square. So, but how this come? That is important. If the function is given, how do you determine? I will explain with an example. Okay. Let me. This is an example of some divide and conquer problem, and the time complexity is log n, because n is equal to n by 2. So a time complexity, when we are dividing the problem, so its time complexity is order of log n. Another function, it is a factorial function. You know, it is a very common function. Recursive algorithm. For it is a recursive algorithm, the algorithm is the what? The Fn is equal to, there is a function, factorial function Fn, and if n is equal to 1, then return 1, else return n into fact n minus 1. So time complexity is what? It is a Tn is equal to a, or some any value constant for n is equal to 1, because Tn is equal to constant for n is equal to 1, and Tn is equal to Tn plus minus 1 plus c for n greater than 1, and where a and c are constant. So this is the algorithm from which we are getting the running time of this algorithm Tn, or the how many times a factorial function is called. How many times we are calling the factorial function, that is fact. Again, we analyze this algorithm. Once you know the recurrence equation, that is Tn is equal to Tn minus 1 plus c, we can determine the recurrence of these. Let us discuss through stylus. Then you can only understand. Okay, let me explain these things. অন্য জিনিসও শেয়ার করতে পারি, এটাও থাকবে, এটাকে বন্ধ করতে হবে। শিল্পী শিল্পী স্ক্রিন শেয়ার কি করতে হবে না, এটা ইয়ে করে বল না শিল্পী। লিখি এখানে কি করে স্ক্রিন শেয়ার করে না, যখন লিখবো ইয়ে না স্ক্রিনে হবে তো, লেখাটা স্ক্রিনে হবে না, স্ক্রিনে হবে, প্রবলেম। Asymptotic notation suppose asymptotic notation এটা ইয়ে আসছে, মোটাটা কম করে কি করবে, মোটাটা কালার কালার আর একটু পাতলা করার জন্য এটা ইরেজার। So we have a big O notation. Okay, let us take any function. If we say function is like fn equal to suppose 2n square 3n plus 2. Okay, any function is given and I have to find out to suppose to prove that fn equal to big O of n square. So what you do in order to find that, the fn is said to be big O of gn. So here clearly how do you get the gn is clear that here gn is equal to what, gn is equal to n square, no problem. But we have to satisfy the inequality, that is your inequality is what, fn is your less or equal to cgn for all n greater than equal to n0. That is it, and n0 is positive constant and c is also positive constant. So this is the inequality we have to do. Then we can say that fn is equal to big O of fn equal to big O of gn. The fn is equal to big O of gn only when this inequality satisfies fn is less or equal to cgn. Now how do you do this? Fn is equal to 2n square plus 3n plus 2. How do you do this? So for this we can easily find this fn equal to 2n square plus suppose 3n plus 2. Okay, now very things where we can directly find there are no unique analysis of this algorithm. So suppose you know this is less or equal to, we can say it is 2n square plus 3n, and if it is suppose 2 is replaced by n, 2 is replaced by n for all n your greater than equal to for n greater than 2. Okay, and replace 2 by n for n greater than. So this becomes what? It is 2n square plus 3n plus n, 3n plus n. This is 4n. Okay, now I want to replace this is n square, 2n square. Okay, now I want to replace 4n by n square, 4n by 4n square. So for what value of n square? If I say I want to replace the n square, okay, and for what value of n square is greater than equal to 4n. Okay, so if n again, if it is n is 2, n is 2, both are equal. 2 square 4 is, for n equal to 2, both are equal. 4, no, for n is it is not 2. For n is equal to 3, 9, and it is 12. Okay, for n equal to 2, it is for n equal to 2, it is 4 is greater than equal to 4, not possible. For n is equal to 3, it is 3 into 3, 9, 9 is 12, not possible. For n is equal to 4, yes. For n is equal to 4, if I put n equal to 4, so it is 16 greater than equal to 16, true. And when n is equal to 5, so obviously it is what? When this can be replaced by n square. Okay. So this is for all what? N is greater than equal to, n is greater than equal to 4. Now this is what? This is less or equal to simply n 2n square plus n square, it is 3n square. So what you get? Finally we'll get fn is less or equal to, okay, 3n square. 3n square. And when we write this, it is in the form of fn is less or equal to cgn. So we can write this is fn, therefore we can write it is fn equal to big O of n square. Okay, for all, this is true for fn is less equal to n square for all n is greater than equal to 4. So where c is equal to what? C is your 3, and the value of n0, the value of n0, this is the value of n0, the value of n0 is equal to 4. So whenever we can show this in a way, how do you determine the time complexity of any function or of any algorithm, or any algorithm? From algorithm we can determine the function, and if the function is given directly, we can find the time complexity or in big O notation, time complexity or big O of n square. So normally whenever the time complexity, if it is a quadratic, it is a what? Quadratic function, so definitely its time complexity will be quadratic, order of n square. So in this way, we can find the time complexity of any function. Maybe it is a quadratic function or exponential function, or it is a cubic function. The method is same. In the same way, you can just you have knowledge of what? Inequality. So if you have the knowledge of inequality, you can easily find the time complexity of any function. Yeah, in the form of big O notation. So big O of n square. Okay. So first coefficient is C there. Always finally the fn is less or always it will be the greater 3n square. That means what? The maximum we can find it is always it is the whatever the value of C, it will be greater than the coefficient of the n square in the given function. So that is the main thing. That is true and 3. It cannot is always greater than the coefficient of the highest degree term. The highest degree term is your n square. Here the highest degree term is n square. So what is the coefficient of the highest degree term? 2. So finally in the inequality, it should be the greater than the coefficient of the highest degree term, that is 3n square. And that is the best analysis. It can be 4n square, it can be 5n square. The maximum may be fn is equal to maximum maybe what? 3 2 into 6. Maybe it is 6 n square. It is also true. This is the inequality whole. But this is the better analysis. Fn is less or equal to 3 n square is the better analysis. Then Fn is equal to less or equal to 6 n square. Okay, we are counting the coefficient, simply coefficient. 3 plus 2, 5, and for this it is 1. So 3 plus 2, 5 plus 1. So that is the maximum. So Fn is equal. But the better analysis is Fn is equal to less or equal to 3 n square. So this is the big O. In this way, you can perform the time complexity of this. Now, suppose you are having the different algorithm. If you know that this is the iterative, I'm talking about the analysis of the iterative algorithm, which function is given. Now, let us discuss the algorithm, the recursive algorithm. Recursive algorithm. You know that there are so many recursive. How do you analyze the recursive algorithm? How do you analyze the recursive algorithm? That is my question. Okay, I am erasing this. এটার থেকে তোর ওইটা ভালো জানিস তো let us take the analysis of a recursive algorithm. Recursive everybody know the factorial function, how to analyze the factorial function, because you are aware of that. The factorial function, we know that is a any function, or you know the tower of Hanoi problem, recursive algorithm, or the factorial function, or Fibonacci function, how to find the time complexity of those algorithms, because those are recursive algorithms. Suppose for factorial function, what is the recursive algorithm? Do you know what is the recursive algorithm of the factorial function? The code is very simple. We can, if you write the algorithm of it, suppose it is a factorial function fact n, and this is if your n is equal to 1, then we can return 1, else we can then return n into return your n into fact n minus 1. So this is very simple algorithm. So when we perform the analysis of this particular algorithm fact n, the fact is the your name of the algorithm, and we are passing the parameter your n. So when the value is equal to n equal to 1, we return 1, and else return n into fact n minus 1. So this is the algorithm, and the formula, the basic formula is what? If any function fn, which can be written as a factorial function n, and this value is equal to your, it is 1, its value is equal to 1 if n is equal to 1, and its value is equal to your n into it is f n minus 1 if it is n is greater than 1. So this is the formula, basically mathematical formula. If the fn is equal to factorial of n, and it equal to 1 if n is equal to 1, and it is equal to n into f n minus 1 if n is greater than 1. Now how do you perform the analysis, complexity analysis, or the time complexity analysis of this algorithm? So the time complexity function, suppose if it is denoted by tn, so it is the first the how many times the factorial function is called. Okay, this is a n minus 1 times fn, so it is a t of n minus 1. N minus 1 times we're calling, let's say fn minus 1, n minus times we're calling, and there is a multiplication operation in each operation, the n into n minus 1. So for that it is 1. For this it is 1. And the base case, that this is the way by which we can perform the analysis. You have to, whether again there is a step to perform the what analysis of the recursive algorithm. So for the recursive, again you have to know the n, what is the size of input n. Then you have to count the basic operations here also. Then what is the recurrence? You have to find the recurrence or recurrence relation, and this gives the recurrence relation. Tn is equal to Tn minus 1. So Tn is the function, and Tn, the for recursive function, the function call itself repeatedly. So how many times you are calling the function itself? That is n minus 1 times f n minus 1. Then why it is plus 1? Tn minus 1 times we are calling, n minus 1 times we are calling, and the plus 1 is the multiplication one, that the plus is used, plus 1 is used for every times we are multiplying fn minus 1 with n, and there is a multiplication operation. This plus, that's a plus 1. For multiplication it is 1. So, and the base, this is the recursive step, and the base step is what? Basic step is t1 is equal to 1, because when when n is equal to 1, and that is tn is equal to 1. Or if you say if there is no multiplication here, then sometimes we can, because when n is equal to 1, multiplication doesn't take place, so it is simply we can put t1 equal to 0. So if there is no multiplication, so how many times multiplication is take place? For this plus 1. Okay, and if there is no multiplication, then t1 is equal to 0. So using this, now we need to solve this is your base case normally, or basic step, or it is recursive step. The basic step, and this is your recursive step. Recursive step, basic step, and recursive. Now we have to solve this using, there are various methods by which a recurrence can be solved. The various methods are, one is the substitution method. Second one is your iteration method. Third one is your recursion tree method. Recursion tree method. And the fourth one is the master method. So by using any of the method, you can solve the recurrence. But these two methods can have some standard format. All the recurrence we cannot solve using your iteration method or recursion tree method also. But these three methods can have some standard format. And what is the standard format by which these methods can be applicable or used? And that the method for this method number 2, 3, 4, the function that can be written in the form of blip. Then Tn is equal to a t your n by b plus your fn. Okay, if the function is like this, Tn is equal to a times Tn by b plus fn, then only we can use this method, either iteration method or recursion tree method or a master method. So it is not like that, Tn is equal to Tn minus 1. So substitution method is good for solving such type of recurrence. Tn is equal to Tn minus 1 plus 1. So that's why, because there is huge syllabus, we cannot explain all the things in detail, but you should know method, how use a particular methods for a particular type of problem, because there are different types of recurrence equation. So we should know what kind of method should be used for solving that. Okay, so for last three methods, second, 3, 4, there is a standard format of recurrence, that is Tn is equal to, for example, we can have like problem, if we are talking of the merge sort, then there is a, Tn is equal to 2 times Tn by 2, for example, n plus it is your n. But example of it is a mark short. Tn is equal to 2 times Tn by 2 plus example of mark short. Maybe some different also some other case Tn is equal to your 8 times Tn by 2 plus n square or plus theta of n square or simply or function of n square. And this is an example of matrix multiplication. Matrix multiplication simply using divide and conquer. Using divide and conquer, the recurrence is Tn is equal to 8 times Tn by 2. So for this type of recurrence, we can directly, very simple to use the master method. Using master method, we can easily solve using these recurrences. Okay. Also iteration method little bit longer, or recursion tree is a tree kind of method we can solve. But most popular one is the either you can use master method directly, or iteration method. Sometimes we can use also method. Don't use substitution method. Substitution method is the theory is not very straightforward. So you have some another concept behind it. That's why we do not prefer substitution method, because it depends on the some guess, initial guess, for which you need to find the solution. So sometimes we do not prefer this substitution method. So let us solve any problem related to this. Now, see, there are, the methods are these are the part of analysis. These are part of analysis. There are a lot of things need to know about the analysis. The main things is to know what you first know the asymptotic notations. Okay, the very first is to for analyzing the algorithm. এখানে না ইয়ে হয় না কি করে না বেকার এটা তো কাজই করে না এই যে মিস্টার শিল্পী বার করে দিয়েছে এই লেখাটা হ্যাঁ এটা কাজই করে না এখানে তো অন্য পেজটা দেখান দাও অন্য পেজটা খুলো শিল্পী এটাকে বন্ধ করে দিই কি করব গুগল করে না হ্যাঁ কি করে হবে অন্য পেজটা খুলে দে বাবা যেখানে এটা বন্ধই করে দে মানে এখন স্লাইড শেয়ার করব তো এটা রিমুভ করব না এটা রিমুভ করে দে এই তো দাঁড়াও না কোনো কাজ করছে না ছেড়ে দাও তো কমপ্লেক্সিটি নিয়ে হয়নি বাবু ওটা অন্য আমি দেখাবো এখন ছেড়ে দে অন্য শেয়ার করবো শেয়ার স্ক্রিন শেয়ার So let us now discuss, because there are a lot of things you need to know about the analysis. The very first is the knowledge of your asymptotic notations like BIGO notations, other notations also there, your omega notations or big theta notations, but normally you perform the BIGO notations. Then you have an idea of your loop, some loop complexity, how to get the function or running time, and how to analyze the recursive algorithm. The recursive algorithm, the most commonly used recursive algorithms are your Fibonacci number or factorial number, tower of Hanoi problem. Sometimes many problems you can solve using different design technique also for recursive algorithm. Now I'm I want to discuss some design technique. There are various design technique, algorithm design technique. Starting with a very brute force technique, brute force design technique, under which we can have many problems like selection sort, okay, bubble sort. You are aware of that, selection sort, bubble sort. That comes from the brute force. It is a very straightforward approach, and we can easily solve the problem. Hmm. Sequential search, also the linear search is also there, simple. Then exhaustive search technique is also there under brute force. We can solve using exhaustive search like traveling salesman problem, knapsack problem, assignment problem, like that. Now come to the another design technique, that is your divide and conquer. That is the most popular design technique, divide and conquer. And the time complexity from the problem which you can solve using divide and conquer, the time complexity, either it is a big O of n log n or log n. And the problems we can solve using this technique is your merge sort, quick sort, binary search, matrix multiplication. And the time complexity of these are either log n and log n, or for it is, if it is a binary search, it is order of log n. Extraction multiplication, the time complexity is order of your n to the power 2.81. The other design technique, the most common one, I will discuss because in many some design techniques are there in which you can solve the optimization problem. And this is a greedy technique, one of them, in which we can solve the optimization problem, some of the optimization problem. Now let us discuss under greedy. What is greedy? Basically, the greedy technique is general design algorithm design technique built on the following elements: pseudo configuration, different choices, and value to find. And there is a, for every object optimization problem, there is an objective function. The sum of configuration to be either maximize and the purpose of the objective function is to either maximize the problem or minimize the problem. There are many problems which are maximization based or minimization based. Now here the greedy is not again depends on the some greedy choice, or we have need to we have some initial values or initial guess, and that is local one, and we check whether finally that local choice can be optimal or not, and that is the main challenging task here. Okay. The problem which you can solve using greedy strategy are your change making or change coin making, the minimum spanning tree, and then shortest path problem, that is a single source shortest path problem. Then Huffman codes are some of them. Also some approximation problems are also there. We can solve traveling salesman problem or fractional knapsack problem. So let us discuss very commonly used problem is your spanning tree problem. Now what is spanning tree? What is spanning tree? The spanning tree, it is not a tree. Whenever we're talking about the spanning tree, it is not basically, it is a tree, but it is a tree of a certain graph. Now suppose you are given a graph. So a spanning tree is what? So a spanning tree is nothing but it is a subgraph of a given graph. It is a subgraph, or it is a tree of a given graph which contain all the vertices of the given graph. So this is a graph. Now spanning tree, we can form a different spanning tree. See here. This is a graph, weighted graph, because every edge consists of certain real values, all the edges. Now the tree contains all the vertices. So how many such trees can be possible? The only the criteria, all the tree should contain the given vertices of the graph. So there are 4 vertices. So for all the different trees, see, and all the trees contain the given number of vertices of the graph. So, but we can take different edges. So how do you form a different tree? So you select different edges, but in all the trees, 4 vertices are there. There are 4 vertices of the given graph. So in all the trees, 4 vertices must be there. The edge can be different. You can take any number of edges. But for any graph or the definition of trees here, if there are n number of vertices and n minus 1 number of edges, then that is always a tree. But what is the properties of the tree? If there are n number of vertices and n minus 1 number of edges, then that graph is always a tree. So here there are 4 vertices, 3 number of edges. In all cases, see there are 4 vertices and 3 number of edges. Okay, but in the given graph, there are 4 vertices and how many edges are there? 1, 2, 3, 4. 4 edges are there. So it cannot be tree. It is a graph. But in order to, a graph can be a tree only when if the number of edges should be 1 less than the number of vertices. So we can form 3 different number of spanning tree. We can form them. Now we can find the sum of the weight of the edges of all the tree. Sum of the weight of the edges. In the first graph, it is sum of the weight is 9. In the second graph, the sum of the weight is your 8. In the third graph, the sum of the weight is 6. So what is now from here? We can find that we can form 3 spanning trees. We can form 3 spanning tree with different sum of the weight of the edges. So that's the concept of minimum spanning tree comes. Minimum spanning tree. So what is the minimum spanning tree? The minimum spanning tree is a kind of tree whose sum of the weight of the edges is minimum. Okay, we can form any number of spanning tree from the given graph. We can form any number of spanning tree from the given graph. So we can calculate the sum of the weight of all the spanning tree. The weight of the sum of the weight of the spanning tree, or the weight having or the tree having the minimum weight is called the minimum spanning tree. Now, how do you determine the minimum spanning tree? How do you determine the minimum spanning tree? There are 2 algorithms for determining the minimum spanning tree. What are those? One is called, these are the applications of the minimum spanning tree for network design, or what are the applications of minimum spanning? Network design like telephone, electrical, hydraulic, TV cabling, computer network, like that. It's approximation algorithm for NP-hard problem, like traveling system problem. This for cluster analysis we can use also, for reducing data storage in sequencing, for learning talent features or real-time face verifications. There are a lot of algorithms of minimum spanning tree, mainly for use for network purpose, network design purpose. Now there are 2 algorithms for solving this problem or to find the minimum spanning tree. The very first one is the Prim's algorithm. Now, what is the Prim's algorithm? This is the algorithm because we need to know the algorithm for solving the problem, or need to know the procedure to solve the problem. The algorithm always represent in a different form, or pseudocode format for its analysis. But in design technique, most of the design technique, the understanding of the algorithm or understanding the procedure is important to solve the problem. The analysis mainly depend on the number of vertices and the number of edges of the graph, because it is a graph. It is a graph. So how many vertices are there and how many, the time complexity depends on that, the number of vertices and the number of. Later on I will discuss what is the time complexity. Let us solve a problem by using Prim's algorithm. So this is the graph, and we want to solve this minimum spanning problem using Prim's algorithm. So this is a weighted graph. The weighted graph, and I want to find the minimum spanning tree using Prim's algorithm. So how do you solve this? Say, because the tree should contain all the vertices. Okay, tree. So all the vertices, we can start with any vertex. We can start with them. Suppose let us start with the vertex A. Mute So here in using Prim's algorithm, because the trees should contain all the vertices, so we can start from any vertex. The tree vertex, suppose we start with vertex A. So the remaining vertices are B, C, D, E, F. Now the vertex adjacent to vertex A are B, F, and E. That means adjacent means it is directly connected with the vertex A. So B is directly connected with A, F is directly connected with A, E is also directly connected with A. Okay. So what you, if you see the under the column remaining vertices B, C, D, E, F, and B is adjacent to A, F is adjacent to A, E, N. So B, A, the weight is 3, and C is not directly connected with A. So the first uh, value here, it is blank, because there is the weight is blank because it is not directly connected. And because that means the first is the vertex connected with that vertex. So obviously C is not directly connected with A, so it is dash blank, and we put the very large value for it, that is your infinity, if it is not directly connected. And D, again for the D, it is same case. D is not directly connected with A, so D dash, because it is not adjacent to A. D is not adjacent to A. Any vertex is adjacent to A if 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 it is directly connected with that vertex. Okay, that's why D is not directly connected with A. C is not directly connected with A. So C is not adjacent to A. D is not adjacent to A. So that's we put blank here, dash here, and the value is a very large high value, that is we set normally it is infinity. But E is directly connected with A, E, and the weight is 6, and F is directly connected with A, that is the value weight is 5. So from here we find the minimum weight. From here we find the minimum. The minimum weight is 3. Minimum weight is 3. So we draw an edge. We draw an edge AB, because 3 is what the weight 3, that is being reached for the your edge AB. So we draw the graph, that is your AB. Okay, AB, and because 3 is minimum among these, 3 is minimum. Now when we take B, now B comes to the first column, that is BA3. Now next time it is T in under T vertices column, it is BA comma 3. It is BA comma 3. Now once any vertex is considered, so that vertex again it is not a part of remaining vertices. So when B is considered and A is already considered in the first step, so in the remaining vertices, the other vertices, remaining vertices are C, D, E, F. C, D, E, F. Okay. Now again, check which vertices are adjacent to B. Which vertices? C is adjacent to B. C is adjacent to B, and its weight is 1. C is adjacent to B, and its weight is 1. D is not adjacent to B, so it is infinity. D is not adjacent to B, so D is infinity. Now E is adjacent to, now see E. Now E is previously E. Okay, why it is A comma 6? Because we are not taking the adjacency of directly. Previously, E is adjacent to A, so we just copy that one, E A6. And then similarly for the F is already adjacent to A, because it is already that A is already in the graph, so it is adjacent to A. Yeah. So FB, we just only copy the last two, EA6 and FA5. But the value can change. Why? The FB, if you see the FB, and it is 4. Why it is 4? Why it is 4? FB, it is 4, because the weight is here. It is FB. It is when we take the F. Now there is a direct F is adjacent to B, so FB is equal to 4. Also F is adjacent to A, but in the first step it is F is adjacent to A, so it is FA, and in the next time, because F is also adjacent to B, so it is FB is equal to 4, because the weight is 4. So now we can again we pick the minimum one. The minimum one is CB comma 1. C be equal 1. So next time we draw an edge that is BC. Draw an edge. We draw an edge BC. Okay. Now from here the in the tree vertices column that is B C B comma 1. So C B comma 1 it will come to the first column. C B comma 1 will come to the first column. C B comma 1. So now again from where the remaining vertices are D. So D now see the value of D changes here. Now D is adjacent to C. So D is adjacent to C because it is directly connected. The weight is 6. The weight of CD edge is 6. E is EA, so there is no change because E is already is connected previously, but previously visited or considered vertices. So EA there is no change, and FB it is all again it is copied from the previous iteration. FB is equal to 4. So from here again you repeat the process. Which one is the minimum? Clearly FB4 is minimum. So here we draw BF and the weight is your 4. So we continue the process in the similar way. Now BF4 come to the first column. FB4 comes to the first column. The remaining vertices are D, F, D. Now see here D, F, 5. Why D, F, 5? If you see the FD, because D is adjacent to F and the weight of FD is 5. The weight of the DF, when we're taking the DF, the weight is 5. And EF, because E is also adjacent to F, E is also adjacent to F, and the weight is 2. So EF is equal to 2. So we have basically updated whenever we get the adjacent of the selected vertices, that is your F is our selected vertices. If any vertex which is adjacent to that, so we take the weight of it. So because E is the adjacent to F, so the weight of weight of EF is your 2. So now from here the minimum one is EF, minimum is 2, and the edge is your EF or FE. So you draw FE edge. We draw FE edge. Next time again this EF2 comes to the first column. EF comes to first column. The remaining vertices is D, F, 5. So here only we need to draw the last one D, that is D, FD edge, that is FD edge, and the weight is 5. So that means all the vertices have been considered. Finally D, F5 come to the first column, and no vertex remain to scan. No vertex remain to scan. So algorithm stops since all the vertices are included, because the spanning tree contains all the vertices of the given graph. So at 1, 2, 3, 4, 5, 6, there are 6 vertices, and all the vertices are included, and the algorithm will stop, and you find the sum of the weight of these edges. And this gives the value 15. 3 plus 1, 1 plus 3, 4, 4 plus 4, 8, 8 plus 2, 10, 10 plus 5, 15. So the sum of the weight of, so this gives the weight of the minimum spanning tree. So this is the Prim's algorithm. Now if you're talking about the efficiency, if it is an unordered array, the array can be ordered or unordered. If it is unordered array, the efficiency is order of n square. Because the number of vertices and your number of edges, it is n into n. It is unordered one, and it's a binary heap. The efficiency when we're talking about binary heap, this is binary. Obviously, there is logarithmic time complexity. So it is a m log n, where n is the number of edges, and n is the number of vertices, and m is the number of edges. And if it is a mean heap, the efficiency is your, because n is the number of nodes and m is the number of edges. So when we are talking about the mean heap, there is a max heap and there is a mean heap. And if you have to consider the mean heap, the efficiency is n plus m log n. So this is the now what are the important things about this? The Prim's algorithm is vertex based algorithm, because every time we are picking the vertex, vertex, 3 vertices, and we draw the graph. So it is vertex based algorithm. It is a vertex based algorithm. First, the Prim's algorithm need priority queue for locating the nearest vertex. We need to priority queue for locating the nearest vertex. The choice of priority queue matter in Prim's implementation. Now there is a array, the optimal for dense graph, and binary better for the sparse graph. and Fibonacci based in theory but not in practice. So these are the some conclusion of the Prim's algorithm, and there is different algorithm, that is a Kruskal algorithm. The Kruskal algorithm is different than your Prim's algorithm. In Kruskal algorithm, what we do, the weight of the edges are basically first we write them in ascending order. This is the method. Sort the edges by increasing weight, the main things, and we pick a edge after another edge. Okay, so this is again we're considering same graph. So first we list the edges and their weights, and in the you write them in ascending order of the weight of the edges. To see the edge sequence change here, and we write them in ascending order weight starting with minimum to maximum. Okay, now we start in the according to this algorithm, we start with the minimum edge. So first we should draw the edge BC. First we should draw the, because initially we take, because the minimum spanning tree should contain all the vertices. Minimum spanning tree should contain all the vertices. First you draw all the vertices A, B, C, D, A, and start with the minimum edge. So the minimum edge is your BC. So first you draw BC edge. The next minimum is EF. So next we draw the EF edge. See there. The next time we draw the EF edge. Next time in the third it is AB. Draw AB edge. Draw AB edge. Okay. Then come to it is the draw BF edge. Draw BF edge. Okay. Draw BF. Okay. Then come to after draw BF. Then CF. Can we draw CF? No, we cannot draw CFS, because in this case there is a circuit will be formed. So there should not be a formation of circuit. You remember, but tree is a acyclic graph. Tree is a acyclic means tree is a circuitless graph. Tree never contains circuit. Circuit is basically closed loop. So tree it is a acyclic or it is a circuitless graph. So there should not be formation of loop in any stage. So we cannot take CF edge. If we take CF, it will form a loop. So CF will not be. Then AF. Can we take AF? AF, yes, we can take AF. In the next step, we can take AF. No, we cannot send BF after. We cannot also take AF. If we take AF, again it will form a loop. So we cannot take AF. Can we take DF? DF. DF. We can take DF. See, we can take DF. So by taking this DF, all the vertices, we start with all the vertices, and the number of, because the number of vertices are 6, so the total number of edges should be 5. So here the number of edges 1, 2, 3, 4, 5. So since all the 5 edges are included, all the 5 edges here, so algorithm we stop the algorithm. We stop the algorithm. So just we need to check carefully at each stage circuit should not be or cycle should not be formed. But tree is a cyclic graph. Now we can find the sum of the weight of the edges, and again it will give the 15. Because whatever the algorithm, whether it is a Kruskal algorithm or Prim's algorithm, the weight remains same. So the total weight again it is 15. But the difference between the Prim's and Kruskal is a edge-based algorithm, and whereas your Prim's algorithm is vertex-based algorithm. Prim's algorithm with a heap is faster than Kruskal algorithm. But if you compare these two algorithms, which one is faster? If we take the Prim's algorithm with heap, so it becomes faster. Otherwise, Kruskal is easier than Prim's algorithm. So these are the two problems under your this greedy technique. The problems which again we can solve some other shortest path problem. This is a C here. We can have a Dijkstra algorithm that is a single source shortest path problem. Now here efficiency, again not forget this. Efficiency of this algorithm is because it is a edge-based algorithm, so efficiency is big O of E log E, and previously it is M log E, M log M. Now it is a E log E, where E is the number of edges. So efficiency of this algorithm is order of E log E. Now Dijkstra algorithm is used for finding the shortest path, single source shortest path problem. The shortest path problem is a kind of problem in which we can find the shortest path between two vertices. And again, it is a weighted graph for which you can find the shortest path. But the important thing is here we should know the destination, the source vertex, and from the source vertex we can find the shortest path from source to any other vertex. So single source shortest path problem. So this algorithm is used for solving this single source shortest path problem. So this algorithm, the method is like this. We can solve the same problem. That's a previous problem using shortest path problem. This is a algorithm here. Graph. This is a graph is given. So we have to find out there is a formula. With that is initially that your distance matrix. We have to find the distance matrix, that is dx, and initially dx is equal to weight of the weight of Rx, dx is equal to weight of, that is the when there is an Rx, then Rx, if there is there exists an age, then we can, there is a W of Rx, and otherwise dx is equal to infinity if there is no age. So and other if there, and we can make another vertex which is temporary, that is y. So dy, that is a distance from source to that vertex y, distance from source to vertex y, that is minimum of dy plus dx plus wxy. So this is the formula for finding the distance from source to the vertex y. Distance, first we find the direct shortest distance from source to direct shortest distance from source to other vertices. So here using this algorithm, and if your source is A, we can find our shortest path from all other vertices. We can find the shortest path from B to A. We can find shortest path from C to A, F to A, D to A, or E to A. So this is the algorithm, because the source must be known. Then we can only find the shortest path from source to the remaining vertices or other vertices. But using this algorithm, we cannot find the shortest path between any pair of vertices. That is not possible. Using this algorithm, we cannot find the shortest path between any intermediate. Suppose I want to find out the shortest path between B and D. Not possible. Using distra, it is not possible. Distra, for distra, we must know the source vertex. If which one is the source, then only you can find the shortest path. So this is the your algorithm I am explaining. Okay, initially what happened, that is initially your distance. Suppose here if your A is the source vertex, so initially dA is equal to 0, and this is the initialization, and dB is equal to infinity, DC equal to all the remaining. Initially we set them very large values, that is dB, DC, that is the direct shortest distance from source to B, source to C, source to D, source to E, source to, that is infinity. We set first if we start from the source vertex A, first it is 0, and rest are infinity. And this is a path matrix. This is a D is the path matrix for this, or is P, A, B, C, all are null. So just you just repeat the same way in which the minimal spanning tree is solved. First, three vertices is your A. So we start with because there is no weight, because we are starting with A, there is no weight attached with A because A is the source vertex. So A, comma 0. Then the remaining vertices are just like your minimum spanning tree problem, is whether it is a Prim's normally we are using the Prim's algorithm. It's very similar to Prim's algorithm. The remaining vertices are B, C, D, E, F, and you see the infinity is that where no adjacencies. For C and D, C and D are not adjacent to C, and D are not adjacent to A, so it is infinity. And your B, E, and F are adjacent to A, B, F, so its value is given there. Distance, now it is the distance and path vertex, or distance and path matrix, you can say. So D is equal to 0, and dB is equal to what? Distance of B, that is distance from source to vertex B, it is 3. Distance from source A, so source vertex is 0A, and A to B, the distance is 3. So it is dB is equal to 3, and DC and DD, because C and D are not directly connected, so it is infinity. So it is infinity, and E and F, it is 6 and 5. For E it is 6, and for F it is 5. Okay. Now the path, about the path, now P is equal to A. Okay, and PB is equal to initially PA is equal to null PB, but now when we start with the vertex A, so PA is equal to A, and PB is equal to A because we have considered the AB. Because we consider the AB, so PB is equal to A comma B. PC is your null, PD is equal to null because C and D are not adjacent to A, and P is equal to A comma E, and PF is equal to A because E and F are directly connected with A. So P is equal to AE and PF is equal to A. Now, in the three vertices next time, and we consider because the minimum is your B A comma 3, so it comes to the first column B A comma 3. Now we are updating this the remaining vertices here. So now we want to find out the BA. Now see here BC. Now BC. Now we want to calculate the shortest distance, direct shortest distance from A to C, and from A to C is what? The use this formula, the D when Y, replace Y by C. That means distance of C is equal to minimum of distance of C. Okay, minimum of distance of C plus distance of X plus X, this XY. So it is nothing but is a so minimum. Now it is a, suppose I want to calculate the, this is the minimum of P. The D of B is equal to what? D of B is equal to minimum of D of B, that is 3, comma, that is D of B dx, okay, and plus your P plus C, that is 3 plus 1 is 4. So D of Y, that is when the Y is the, Y is previously it is infinity because C is not directly connected. So D of Y, here in Y it is C. The D of C is equal to minimum of D of C, that is infinity, comma D of B, direct distance of D of B plus weight of XY means weight of BC. So infinity comma minimum of infinity comma 3 plus 1 4. So minimum is 4. So here it is minimum is your 4. If you see here D of C is equal to 4. That is CB and it is 3 plus 1. So it is DC is equal to 4. And DD is infinity, D is equal to 6. There is no change. So now when we consider the DC, so now the path is BC, that is A comma B comma C. You see the path matrix, it is A comma B comma C. So it is A, B, C. Okay, that means the from direct shortest distance from A to B it is 3. Now from A to C it is 3 plus 1, it is 4. Because we are every time we are calculating the shortest distance from the source vertex. The source vertex is blue color, that is your A. Source vertex is your A. Now next time from here we pick the minimum, that is DC is equal to 4, and it is CB comma 4. So it comes to the first column CB comma 4 because the minimum is CB comma 4. So CB comma 4 comes to the first column. Now again the remaining vertices becomes DEF. So we have to update your DC. So how do you update the DC? Now come to, if you see the graph, so that is DC, the CD distance. Okay, D. Now we want to calculate the shortest distance, direct shortest distance of D. So earlier it is infinity. Okay, so infinity, and now it is shortest. The minimum of your minimum dy is equal to minimum of dy is infinity, comma d of x, that is your C, and it is your 3 plus 1 4, 4 plus 6 10, 4 plus 6 10. So obviously direct distance from source to D, it is 10. So that is your 4 plus 6 10. So see here it is 4 plus 6, D comma C, it is 4 plus 6, it is 10. So D of D is what? 10. Earlier it is infinity because there is no directly connected with the your earlier vertex. So DD is equal to 10. Now it becomes PD is equal to AB comma C, A B C D, because T now T is we are considering A B C D. So from here, which one is the minimum? If you see the minimum one is 5, F A comma 5. So obviously we take the this F A comma 5. So this is F A comma 5. So you draw AF, you draw AF edge. That means the direct shortest distance from A to F is your 5. A to F, because every time we are calculating the shortest distance from the source vertex. So source to F is your minimum distance is 5. Now the F 5 is the comes to the first column. The remaining vertices are DC, 10, DC, 10. and EA comma 6. We are basically EA comma 6. We are copying from the previous table, previous iteration. Now here the all are same. See here, DB, DC4, DD10, DE6, and D5. So from here, which one is the minimum? EA6. So we draw A edge. So that means the shortest distance from vertex A to E is 6. Direct shortest distance, it is A to E 6. So next time it is this comes to the first column, EA6 comes to the first column. The remaining vertex is DC comma 10. From where it is the only vertex DC comma 10. So DC comma 10. So finally we draw that is your D, and that is your CD. So CD is what the finally will go, get the shortest distance from A to D. A to D is 10. 6 plus 1, 7, 7 plus 3, 10. So DD is 10, means it is the shortest distance from source to the vertex D. DD means the DD is 10 or DC is equal to 4 or D is equal to 6. It gives the direct shortest distance from A to this vertex. A to DA means there is no A is the source, so it is 0. So D to B, that means A to B distance is 3, A to C distance is 4, A to D distance is 10, A to E distance is 6, A to F. So all these distances give the shortest distance. So in this way, we can get the shortest, all the shortest distances from the source vertex. So this algorithm stops since no edges to scan. So when DC come to 10, no edge remains to scan, so algorithm is stopped. So this is the DISTA algorithm, very important algorithm for finding the shortest path from source to all the remaining vertices. So this is the now the analysis about the analysis. So the it doesn't work with negative weights. Remember, this DISTA algorithm doesn't applicable for the when the weights are negative. Applicable to both undirected and directed graph. When the it is we consider the undirected graph, so it is also applicable for the directed graph also. When edges are directed, it is called directed graph. When all edges are directed, that is it is a directed graph. So use unordered array to store the priority queue. The efficiency when we use the unordered array to store the priority queue, the efficiency becomes order of n square. And when we use minif to store the priority queue, if you use the minif, then efficiency becomes order of m log n, where m is the number of edges and n is the number of vertices. So this is the time complexity using different methods or different approach. Either you can have an unordered array using priority queue or minif. Both are using priority queue, but using unordered array or minif, the time complexity are different. But which one is the better one? Obviously, it depends on the value of whether if m is doesn't equal to n, if m is lesser than n, obviously the second one is the better one because logarithmic time complexity is always better than the quadratic time complexity. So logarithmic time complexity, so it is faster. The second one, the m log n is always faster than that is if you use the minif. So this one the faster one than the first one, that is using unordered array. So this is the all about your the important design technique, that is your greedy technique, normally used for solving optimization problem, or sometimes it is also for many NP problems or NP hard problems. So this is the one things your about your greedy technique. Now come to another design technique. So this is another design technique, very important one, your dynamic programming. Mm, and dynamic programming is a kind of technique, design technique, which is normally used for solving optimization problem. Uh, the some of the commonly used problem which we can solve using dynamic programming, like your matrix chain multiplication, traveling salesman problem, knapsack problem, we can also solve using this. Shortest path problem also you can solve using dynamic programming. All pair shortest path problem, that is the most generalized algorithm for solving shortest path problem. The dynamic programming is basically a general algorithm design technique for solving problems by recurrences with overlapping subproblems. That is the main things, the difference between the divide and conquer and your dynamic programming. It is invented by your Richard Bellman in the 1950s, and it is mainly used for solving optimization problem. Here, programming means your planning. What is the main idea of to solve any problem using dynamic programming? First, you have to set up a recurrence relating a solution to larger instances to solution of the some smaller instances. Then we solve the smaller instances once. We solve the smaller instances once, then record solution in a table and extract solution to the initial instance from that table. So basically, there is, when we're talking about the divide and conquer technique and dynamic programming, in some cases both are same, and in some cases it is different. In divide and conquer, we divide the problem into the sub problem. Same is the case for the your dynamic program. We solve the sub problem using recursive in divide and conquer as well as in the dynamic programming. But in divide and conquer, we do not store the solution of the sub problem. So that's why every time when we need that sub problem, so every time we have to recompute that sub problem. So it takes the complexity is there in divide and conquer. So we prefer dynamic programming because once we solve the sub problem, we store in the table, so we need not to solve every time. So that is the main advantage of the your dynamic programming over divide and conquer. So your divide and conquer methods, this is your algorithm. It is again algorithm design technique. So it is your bottom up approach. The dynamic programming here a top down approach. With the input is too large to deal with a straightforward manner. Divide the problem into two or more disjoint subproblems. Then we conquer. Then conquer means we recursively solve the subproblem. That is the conquer. And after conquering, we merge or combine the subproblem solution of the subproblem to get the solution of the original problem. So this is an example of the merge sort. This is a very good example of divide and conquer merge sort. This is a simple code of merge sort. And here the subproblems are independent. All the subproblems are all are different. The subproblems are independent, but all are different. But in dynamic programming, the way of improving the inefficient divide and conquer, it's basically improving the inefficient divide where the divide and conquer is not efficient. We normally prefer dynamic programming. By inefficient, we mean that the same recursive call is made over and over. So we do not like that. Every time same function is calling repeatedly. So if same subproblem is solved several times, we can use table. We can use table to store results of a subproblem the first time it is computed, and thus never have to be recomputed again. So once the table is once the subproblem is used, we can store the result into table so that next time we need not to calculate again. So dynamic programming is applicable when the subproblems are dependent. That is when subproblems share subproblem. One subproblem can share the so for solution of another subproblem, we need to use the solution of another subproblem. Now, see, this is the basic difference between the dynamic programming and the recursion. In divide and conquer, partitions of a problem into independent smaller subproblem. Whereas in dynamic programming, partition a problem into overlapping subproblems. Here, we do not store the solution of the subproblem, but in dynamic programming, we store the solution of the subproblem. Your divide and conquer is a top-down approach, whereas dynamic programming is a bottom-down approach. Now, these are the things you need to remember. This is the very first example. If you are talking the suppose we need to solve your Fibonacci numbers. How to solve Fibonacci number? Okay. Here, there is a formula for generating Fibonacci number. Fn is equal to Fn minus 1 plus Fn minus 2. And then F0 is in the initial condition, is the F0 is equal to 0 and F1 is equal to 1. But without knowing that, we cannot generate the next number. So F0 and F1 should be known. The Fibonacci sequence is 0, 0, 0, 1, 1, 2, like that. So once you know the previous two numbers, we can generate the next two numbers. So how to generate the nth Fibonacci numbers recursively using your top-down approach, because this is divide and conquer is your bottom. This is your bottom-up approach. This is a top-down algorithm, divide and conquer. But is a dynamic programming is bottom-up algorithm. So when we solve using top-down, so this is the top-down approach. Fn, then Fn minus 1 plus Fn minus 2. Then Fn minus 1 can be known. If it is known, then you can find it Fn minus 2 plus Fn minus 3. If Fn minus 2 is known, then we can determine the Fn minus 3 plus Fn minus. In this way, we can generate two. But when you talk about the dynamic programming, see here how F6, the value of X6 can be calculated. So F6, that means we can calculate F5. Here there's a lot of recomputations or a lot of recursive call can be removed here. F9, F9, sorry, if it is F6, then it is F7 here, and it is F8. Okay, so here there are a lot of efforts should be put in order to calculate that. So using bottom-up fashions, we can calculate the Fibonacci number easily because we store the solution of the each values or each subproblem. Because F6, if you want to calculate F6, we should not F5. We calculate F5 only when we know F4. So in this way, we can calculate in the bottom-up manner. Another very important problem we can solve is that is a knapsack problem. What is the knapsack problem? What is knapsack problem? The knapsack problem is what? The knapsack problem is your it is a kind of problem in which the number of items are given. Number of items. Suppose there are n number of items, and for all items, their weight and the values are given. The weight and their values of the items are given. So it is a knapsack problem. Is a basically maximization problem. It is a maximization problem. You have to find the maximum value or maximum profit. And there are two types of knapsack problem. One is called 0-1 knapsack problem. 0-1 knapsack problem, that is called binary knapsack problem. And another problem which we call the fractional knapsack problem. Fractional knapsack problem. The fractional knapsack problem, that means in knapsack problem, 0-1 knapsack problem, either we are selecting the problem item or we are rejecting the item. Either we can select or reject. But and whenever we are selecting the items, we are considering it's the total weight. What is the weight of that item and the corresponding value. But in case of fractional problem, sometimes in some states we are not considering the entire weight of that item. So that's why it is called we are taking the part of weight of that item. So that's why it is called fractional knapsack problem. So there are two design techniques by which this knapsack problem can be solved. 0-1 knapsack problem, or that can be solved by using dynamic programming, and the fractional knapsack problem can be solved by using dynamic programming. So see here your knapsack problem, 0-1 knapsack problem, it is not mentioned. So 0-1 knapsack problem, that this is the given table, the items are given. Okay, items are given, first column, its values are given, the total weights are also given, value and weight, and capital W, that is the knapsack capacity, that is the capacity of the knapsack goal. The objective is this problem is to find the optimal subset whose sum of the values should be maximum. That's why it is the maximization problem or optimization problem, and the sum of the weight of the items should not exceed the capacity of the knapsack, and the capacity of the knapsack is given. So that you must remember. So that is the method, dynamic programming, by we can solve using it. But when the capacity is more, sometimes we do not prefer, because if its capacity is suppose W is equal to 5 or 6, we can easily solve it. But if its capacity is more, then the table is longer and it will take more time to solve it, although it gives the optimal solution. Some other techniques are also better techniques also here to solve the 0-1 knapsack problem, that is your branch and bound. But there's so many methods by which we can solve your knapsack problem. Initially, brute force technique is there, because here we need to find the optimal subset. So how many subsets are there? Because the number of items are 5, so maximum number of subset is possible is 2 to the power 5, and 2 to the power 5 is how many subset? 2 to the power 5 is means 32. So 32 number of subset is possible, but you exclude null 5, that is empty set is also a subset of every set, so we can exclude 5. Okay, so this is the there are so many technique. Your brute force technique, using heuristic search technique, you can solve the knapsack problem, 0 knapsack problem. Using dynamic programming, we can solve the knapsack problem. Using branch and bound, we can solve the knapsack problem. So, but the objective is to find the maximum profit and the optimal subset. And then optimal subset, the sum of the weight of the subset should not exceed the capacity of the knapsack. So that is the method. So these are there are so many techniques. So that's it is not possible to discuss all the techniques due to very limited time. Okay. Hello.
Okay, so thank you.
From my side, it is over. If any doubt from the audience,
if anyone has any question, please ask, sir.
Yes, I can ready to answer. Video. Anybody, any questions from? Whether you understand the subject or not? No reply from audience. Shubham?
Okay, sir, I think that it is clear to everyone. So thank you, sir. Thank you for your sessions, and thank you for everyone. We appreciate you being here. Thanks again for joining us today, and we will see you next time, sir. And if anyone has any question, then you can reach to sir.
Definitely. I'm ready to answer anytime. Thank you, Shubham.
Okay, sir.
Thank you.